Hello, this is Ian Woolf, producer of Diffusion Science Radio. This show depends on your support. Please make a donation directly with the PayPal button at www.diffusionradio.com or support Diffusion by downloading a free audiobook from audibletrial.com/science or go to diffusionradio.com/support and click on an Amazon link or buy my nano drones.
Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to Diffusion. Sit back and relax while we inject weird and wonderful science directly into your brain. I'm Ian Woolf. On this edition, space psychology and the Australian Square Kilometre Array pathfinder. But first up, here's the news. Electric field brainwaves. Brainwaves have been detected moving only 10 centimetres per second, which is much slower than the speed of any signals travelling along synapses connecting brain cells or even in the gaps between the connections. Researchers from Case Western Reserve University believe that the brain's weak electric field must be the way the information is carried. The brain's weak electric fields produce the signals measured with an EEG electroencephalogram machine. They've been thought to be caused by brain activity. Now it looks like they may be causing brain activity themselves. The team tested their ideas in the brains of mice. They focused on the hippocampus, the part of the brain associated with memory formation and retrieval. They found that although the brain's own electrical field was very weak, that beginning with a cell or group of cells, the field was able to stimulate a nearby brain cell and the next in a slow wave around the brain. Moving to a computer model, they blocked the electric field and moved the brain cells further apart. This slowed the wave down even further. They saw similar results in the mouse brain, convincing the researchers that they're on the right track. The team speculate that brainwaves spread by the weak electrical field could be the cause of sleep and theta waves associated with memory consolidation and the faster waves of epileptic seizures. Further study of the action of the weak electric field may lead not only to better understanding of the healthy brain, but also to treatments for epilepsy, sleep disorders, and memory problems. The paper was titled, "Can Neural Activity Propagate by Endogenous Electrical Field?" and was published in the Journal of Neuroscience. Adena Silverstein is a psychologist in private practice with an interest in space. She gave a talk on space psychology at the Orbit Oz Space Entrepreneur Meetup held at Fishburners in Ultimo in Sydney. After her talk, while we're surrounded by busy people, I began by asking her, how does psychology apply to space travel?
It applies to space travel in many, many ways. Obviously, specifically to people, because psychology is about people. So we have people going up into space, not just payloads and satellites. So it applies to people in that we have to make sure that people can get on and be happy in space and keep them happy for the whole mission. Whereas without that, without the help, it's very difficult for them to be able to keep going the whole mission.
The original astronauts needed the right stuff, and they were fighter pilots, and they were very aggressive and competitive and risk takers. Is that the sort of astronaut we need now? What sort of person do we need?
Okay, so we still need people who are risk takers and adventurers, and people who know how to do all the engineering things, but we also need people who are able to get on with other people and are able to lead a group of people on a mission.
So we need leaders and people with interpersonal skills.
That's right.
And what are the risks to the individuals who go up into space?
Well, there's many risks. There's radiation. There's all sorts of... There's no oxygen, so you're enclosed. There's a risk of something hitting the spaceship. There's a risk of electricity not working. There's the risks of the people having conflict in space. So if we look at it from the psychology perspective, that's what we're really interested in.
So can people afford to have an argument in space, or do they need to all be really diplomatic?
Mostly diplomatic, but a bit of skills as to how to get through an argument are very, very important.
So interpersonal skills are really important, and I guess as well as all that danger, they have to be able to deal with boredom. And what are the other psychological issues facing an astronaut?
There's the boredom, there's the stress of having to do the tasks, and also the stress of getting on with the other people, the stress of not being with their families and being isolated and being in a very small, confined environment.
So being in such a confined, small space, and with astronauts now being up there for like a whole year at a time, that must be really... Is that something Is there a danger that they'll adjust too much?
Well, yes. I mean, they do come back with some enjoyment and some satisfaction from having been in space. And they can't enjoy it too much in the way that getting back down on Earth is difficult because they have to adjust to being back down on Earth, as well as everyone around them needs to adjust to being back down on Earth, or having the astronaut down on Earth with them.
So what does it take for a crew to work well together?
Well, crew cohesion, which means that they are able to work together, motivated to work together as a team on particular tasks and as a team to get on with each other.
And is that different to the way a team would work together on the Earth?
No, in fact the training, it's very interesting that the training on Earth for teamwork is pretty similar to the ones that would take place for astronauts.
Have the simulations on Earth of space missions turned out to be helpful for the real ones, psychologically?
Yes. The analogues in the simulations have been helpful, as well as we've learned a lot from missions such as missions to the analogues, which are missions to the Antarctic regions, missions under military missions, submarine missions are the very closest to what we can get to space missions. And so the research in space psychology is based on those missions.
And what is it that helps astronauts keep their cool, keep their sanity and stay productive and happy?
Well, a bit of the teachings before, and there's a lot of training beforehand, and teaching on how to manage their emotion, teaching on the other people, about how to get along with the other people, as well as a lot of coaching from Earth and from ground control to when they are in through the mission, during the mission.
So they need a lot of support from the people back on the Earth.
Yeah, that support is very, very important. And of course, the further we get away from Earth, like when we go to Mars, that they're going to have to be self-reliant. That support won't be there. Yeah.
For a little bit of a sideways question, did you see the movie The Martian? And if so, what did you think?
I thought the movie of The Martian was very, very good. I think it really showed someone who was resilient and could actually make potatoes from whatever came out of him. And I think that was a very good way of, right, I'm going to cope, and also illustrated how important the wider community was, because he was doing diaries for them and trying to keep in contact with them in that way. Then I think it's very important that we do consider the human element, because missions can actually fail if we don't consider that human element. There's been, for example, Challenger, apparently it was the human element and the teamwork that something didn't quite work and resulted in what happened, in the tragedy.
Adena Silverstein, thank you very much.
Thank you.
That was Adena Silverstein talking about the psychology of space travel.
In the final decade of the 21st century, men and women in rocket ships landed on the moon. By 2200 AD, they had reached the other planets of our solar system. Almost at once, there followed the discovery of hyperdrive, through which the speed of light was first attained and later greatly surpassed. And so at last, mankind began the conquest and colonization of deep space.
You're listening to Ian Woolf on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com. Matthew Whiting is a researcher at CSIRO Astronomy and Space Science, based in Sydney. He works on the processing software for the Australian Square Kilometre Array Pathfinder telescope in Western Australia. I began by asking him to describe the new ASCAP telescope.
So the telescope is called ASCAP, ASKAP. It stands for the Australian Square Kilometre Array Pathfinder. It's a brand new telescope, so we're still building it, but the first elements are in place and working and being used to do lots of exciting science.
So the telescope, it's a very large array of radio telescopes working together?
Yeah, so ASCAP has 36 dishes. So the dishes are all in place, and we're in the process of fitting them out with these receivers. And so once they're all in place, what you do is combine the signals from each of the telescopes and process them in a way that simulates a telescope as large as the distribution on the ground. And so in ASCAP's case, the maximum separation between telescopes is 6 kilometres. So it simulates, you get the images with the resolution you would get with a telescope 6 kilometres across. So this is the process called interferometry. So it's widely used in a lot of radio telescopes nowadays to give you this extra image fidelity, at the expense of not fully sampling this. You couldn't build a dish 6 kilometres across, obviously. So there are trade-offs, but you have the combination of the sensitivity from the individual antennas plus the resolution from the size of that full array.
And you're expecting to generate an enormous amount of astronomical data.
Well, yeah. So this is one of the challenges of working with ASCAP. So this is in part driven by these new receivers. So the multiple beams that you have essentially operate as multiple telescopes. So we've got 36 beams. It's like operating 36 different telescopes all in parallel. And the large number of antennas also generates a lot of data. So you get the data that you're interested in is looking at the combination of signals from pairs of antennas. And so as you increase the number, you increase the number of pairs by sort of the square of that number. And so going to 36 dishes really generates a lot of data. And so when it's operational, when it's fully operational, ASCAP will generate data at the rate of about 2.5 gigabytes a second. So if you think in terms of DVDs, that's a DVD of data every 2 seconds, or a Blu-ray disc of data every 20, I think it is. A way to visualize that is, if you store this on DVDs, a 12-hour observation. So, we follow a source from when it rises through to when it sets. That would generate a stack of DVDs, I think, as high as Sydney Tower. It's like 20,000 DVDs weighing, 2 tons or so on.
So even in hard disk, like even if you're looking at terabyte hard disks, that's just still an enormous amount.
Yeah, so that observation will be 70 or 80 terabytes, and so that you're getting a couple of those a day. We plan on doing 5 years of surveys at least. So yes, data management is a real problem with this.
How do you manage to store that much information over long periods of time? How big are the hard disks?
So the data that we have goes from the telescope. So we have a machine on site out in Western Australia that combines the signals from the pairs of antennas. This is called the correlator. And then it sends that data over the network using the NBN for part of it as well, down to Perth, where it goes to the Pawsey supercomputing centre. So this is a centre that runs several large supercomputers and several large storage systems. And so we basically will set up processing pipelines there that take the data as it comes and then process that, form images and then catalogues and so forth as we go. I mean, we anticipate ASCAP working as a survey instrument, so it'll be basically surveying the whole time. So for a given observation, that has to be processed in the time that it takes to take that data before it moves on to the next field. So you have that time constraint. You need to process all this data quickly, and then you produce a whole lot of what we call data products, so images and catalogues and some of the calibrated raw data, and then we store that in a long-term archive. And it's really that archive that an astronomer who's interested in studying parts of the sky, that's where they will go to go and get the data.
That's still an astonishing amount of data every day.
Yes, so I mean it's enough that we can't keep all of it. So for the images that and so on, the size of them is smaller than the amount of data coming out of the correlator. We would like to keep all of that data, but it is just much too much to keep. We're talking many tens of petabytes of data over the course of the survey. So we have to sort of make judgments about where we say, no, we can't keep this data. So we sort of average some of it and sort of collapse it down in size and keep those data products, which are potentially useful for some aspects. But for other types of science, you make the image products and then you just throw away the raw data because it's too expensive to keep. The work that I and my team are involved with specifically is on these processing pipelines, and so this is the work I'm presenting at the conference. So we have to process this data, as I said, very, very timely fashion. The multiple beams that the telescope produces, so the wide field, requires particular processing approaches that you need to account for particular effects that only become apparent when you have this sort of wide field of view. So most current telescopes have their very narrow field of view, and you can make sort of approximations in the algorithms you use to make the images that just make the processing a lot easier. This is a bit harder to do once you have these wide fields. And so we've had to write a lot of our processing software from scratch, knowing that we have this particular telescope with these particular requirements, but also the scale of the data. We know that we have to run this on a supercomputer. So the computer we run it on is appropriately called Galaxy. So this is, as I said, at the Pawsey Centre in Perth. It's capable of sort of 200 trillion operations a second, I think. So it has 8,000 processing cores. So we need to utilise all of that. It has a lot of memory, a lot of fast network communication to enable you to process these very large data sets, and then generate these images, run your source finding and quality control software, produce these catalogues that then will be the primary thing that astronomers use.
So is it a different sort of skill to program for these supercomputers, a particular set of languages that you have to learn?
The languages we use are fairly common. I mean, the processing software we write in C++ just because it allows us the flexibility to do this stuff on the supercomputer. I guess there are different things you need to take into account when working on this massively parallel system. You know, you need to know where your memory is, where you're sending bits of code, how you communicate between different processors and so on. So the software that we've put together, you know, is one of only a few packages that are around that have been written specifically for, you know, this sort of high performance environment. Most of the software packages that the astronomers in general would use don't really work at this scale, and so this is why we've had to set out and create our own software. So we're at the point now where we have the first elements of the telescope operational. So the first 6 receivers for ASCAP have been operational for about 18 months. These are the first generation of the receivers, and we've been using that to commission the telescope and do a bit of science. So we've had a few science papers published this year, a few discoveries and things, which has been exciting. But we're also using that to commission our software pipelines, and we have a very talented group of people in the commissioning team who are very experienced astronomers and you know, understand how the astronomical software processing works. And so we're using them to use our pipelines, look at the data, identify, you know, what works, what needs a bit more work, and so on, and then basically use that to improve things and get ourselves set up for the first stage of science surveys that we'll start next year with an array of 12 of the new generation receivers.
Could you tell me about one of the discoveries that you've made so far with this telescope?
Well, one of the exciting things about ASCAP is that it's the site that it's in is called the Murchison Radio Astronomy Observatory, and so it's in the Midwest of Western Australia, a long way from anywhere. And this is specifically because we want to be away from civilization and the amount of radio interference that it generates. All the electronic stuff of life, you know, generates lots of radio waves, and they get in the way of our sensitive observations. So one of our great projects that we've got going on at the moment, and was one of the first papers, was to look in a part of the spectrum, so in a range of frequencies where it's just not accessible from anywhere near cities and so on. Just things like mobile phones and other electronic devices create enough interference that you can't see anything there. So we've been looking at distant galaxies that have black holes in the centre of them, and using the stuff that's around the black hole, which gives off a lot of bright emission, using that as a background source to search for cold gas that's sitting in front of it. And so we discovered one of these that had a large amount of cold gas just sitting in the galaxies surrounding this black hole, and this had never been seen in this galaxy before. And so we were able to, using the ASCAP observation, to work out where that galaxy was, identify this cold gas, and realise, using other telescopes as well, to then explore the surrounding environment of that black hole and look at the gas that's been ejected out from the centre of this. This is a very young system where just in the last probably 1,000 years or so, this black hole has sort of blown out all this gas, and you can see this sort of expanding out. And so you can make this discovery by opening up this range of frequencies that you can't really see at other observatories that effectively. And so this is an ongoing project, and we're actually targeting a whole range of similar sort of galaxies in the hope of detecting a lot more of these, and this will really sort of test out this area of science that we hope to expand as we get the full ASCAP array. Well, so something that's just hot off the press. CSIRO had their award ceremony today, and so the ASCAP team had been nominated for the Chairman's Medal for the development of the phased array feeds, and we won. So this is CSIRO's highest internal award, and yeah, it's the PAF development has been recognised as a really outstanding achievement, and hopefully it will continue to grow and show the promise that we all hope it will.
Well, Matthew Whiting, congratulations and thank you very much.
My pleasure. Thank you, Ian.
That was Matthew Whiting talking about processing big data for the Australian Square Kilometre Array Pathfinder telescope. And that's all from us this week on Diffusion. Would you like to join us? We need more people contributing stories to Diffusion. Send your contributions, opinions, congratulations, helpful suggestions and donations to science@diffusionradio.com. That's science@diffusionradio.com, and please do send me an email so I know you're listening and you'd like to hear more episodes. Please like the Diffusion Science Radio page on Facebook and rate us on iTunes. Tell your friends. Follow me on Twitter @Ian Woolf. Checking production was Charles Willock. I produce Diffusion, which is broadcast around Australia on the Community Radio Network, including 2HHH in Hornsby, Ku-ring-gai, 2NVR in Nambucca Valley, 2XX in Canberra, and 3MBR in the Mallee Border districts of Victoria and South Australia. Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station and also on astronomy.fm. Subscribe to our podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos and videos about this week's show. If you enjoyed the show, then explore more than 700 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords, so you can focus in on the stories you want to hear. Subscribe to the Diffusion YouTube channel at youtube.com/c/Diffusion Radio. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits. Photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.